Hi everyone, my name is Samiur Rahman. Today I'm just going to show you a few results that we have got so far on the project that I've been working. So the project is a collaboration between guidance automation and UCL. So guidance automation, they have made a 24 gigahertz radar to be used for level crossing sensor. So they just gave us the radar and they want us to develop some algorithm where we'll be able to detect targets of interest, say like human or dog or whatever, when they're crossing, and then give us some sort of alarm. So this is just the brief outline. So at first I'll show you a brief description of level crossing, and then the radar specification of the guidance radar, and then the results that we got from the experiment, one at an echoic chamber at UCL and one was here at Garden Square. So let me just show you a video. So this is basically, the video is an interview of network real people. So as the radar will be used by them, so it's better to know how they perceive this technology.
Well, this level crossing is near Ormskirk, and it's one of a new generation of crossings. It's recently been improved, and it's got some fancy new technology. And here with me is Martin Gallagher from Network Rail. And Martin, the barriers are coming down now, and they're coming down dictated by radar?
Yeah, radar. What we've got now is an obstacle detection system, a fully automated system that will scan the crossing once a train is approaching. Will confirm that the crossing is clear of obstacles, vehicles, pedestrians, and then we'll send a confirmation, basically a confirmation message to the signal to then allow trains to proceed if the crossing is clear.
You showed me earlier the white pod over there, which is crucial to this whole thing.
Yeah, the white pod is basically what the technology is wrapped up in, which will then be scanning the crossing to confirm that it is clear of obstacles before we allow trains to proceed. And the step change here is this would have been a manually operated crossing previously, and we intend to roll out perhaps, or plan to roll out over 400 of these over the next 5 years.
Is it an expensive business?
Yeah, for one of these crossings they cost over £1 million, but it's commonplace on the continent and even internationally to have obstacle detection crossings. So this is basically optimising technology to automate and to speed up the process.
So, yeah. As you can see, it's a bit of a lucrative business, so that's why they want to commercialize it now. But in order to commercialize it, they need an embedded software that will comply with the guideline of the motor industry and so on. So that's why they're basically collaborating with us right now. These are the few pictures of the radar. So it's a rotating radar. So that's an advantage because we don't have to do any sort of beamforming or anything. We just scan. And right now, the way it's working is basically to make a TCP/IP connection with the laptop, and there is a LabVIEW program that was actually written by a third party, not by guidance. So, and you can just save the data there, and then you can process it. But eventually, what they want is they want a real-time processing, obviously. So that's another thing that they want.
$1 million or £1 million a copy sounds pretty expensive.
Yeah. I mean, if you just give me half the money, I can just sit there and shout whenever.
Yeah.
So is that for the radar? We pay $1 million.
No,
that's what
that must be the crossing,
Yeah,
the things, and everything else.
It can't be only the radar.
It can't just be the
Sure,
sensor.
Yeah.
No. Oh, you think it includes the crossing guard?
Yeah, well, the barriers,
Yeah.
fitting
But
that in,
not
other
very
stuff.
expensive.
No, it isn't. No.
That's why NASA train is not very good.
The trains are so expensive in this country.
So this is the basic specification. So it's an FMCW radar. So operates at 24 gigahertz with 200 megahertz fluid bandwidth. So the radar has 500 samples per pulse. So it has both up chirp and down chirp. So basically 500 for up chirp, 500 down chirp, and so you process 1,000 number of chirps, and total revolution is 1 second, but it's not, when we did the measurements, it's not like exact. So, and it has 1,024 bearing samples. So the window we get the raw data, we actually get 3 information. One is the IF signal, which is just the DRAM value, and then the bearing value and also the chirp direction. 0 means down chirp and 1 means up chirp. So for 1 second here, we should get, for one scan, we should get around 500,000 samples. But when we process the data, we saw that it actually varies. So maybe the radar is moving not precisely at 1 second, or maybe there is something not exactly precise with the data logger, but that's whatever it is. So we just take care of it during processing. So we can say, we can take anything as a reference. For instance, we can say that we'll take 500,000 samples regardless, or we can actually check the bearing values, 1,024 bearing values, and take certain number of samples for each bearing values. So either way, there will be trade-off, but it's quite minimal anyway. So we are hoping that it shouldn't create that much of a difference in the final image. So then we took the radar to the chamber, just do some basic measurement to see whether we can just see the target. That is FMCW radar, the processing is very straightforward. You just do a Fourier transformation of the range profile. So the more than half of the processing is actually segmenting the data. That's it. So how do we actually read the raw data and so on? So after that is just straightforward processing. So this is, the first one is just a corner reflector, and the second one here you can see, I think around 180, so just facing the opposite side of the radar. It's a human target, the second one. So there wasn't much of a scope to do moving target measuring inside the chamber, but at least we were a bit confident that we can see the target before taking it outside.
What's the horizontal streaks?
Oh, this is just bearing angle. Oh, you mean the bands?
Yeah.
We are not sure. We didn't see these bands when we measured outside.
Yeah.
So there were actually very strong reflections coming from here as well.
Is it the internal walls of the chamber?
Probably we are not sure. We are just attributing right now that maybe some sort of reflection coming from the antennas inside.
Yes.
Yeah, something else. But yeah, we were seeing these bands throughout all of the data that we were processing. So this is the field data, the result from the Gordon square. So this is the radar, and you can see the railings, I guess. I think radar is not exactly 0, so a little tilted. So this was just, we were just checking whether you can see the surroundings at first.
Is that just one scan? You haven't integrated?
This is just one scan, yeah. This is just one scan. A single scan to see whether you can see everything, and everything is working right. This is kind of like the zoom-in version to say, this is a corner reflector here. This is a human target, and I think Paul was standing here. So we just wanted to see that if it actually sees the targets properly.
And the axis there, is it there?
It's bearing, so 0 to 360, and that's the range in vertical.
So what's the rest of the noise, and how do you know it?
This is flutter. This is the other because there are also like this area here are tree and railings. So it's basically, if you go back, so that's the basic clutter. So here you see. So there is no background suppression here. This is just the raw processing. So then we did some moving target measurements, that which was our main goal. So there are 2 human targets walking parallelly away from the radar. So we could, so there you can see here.
How close were they separated, Samiur?
Around, I think,
6 meters.
6 meters, right? Yeah, 6 meters.
How do you sort of record your ground truth? You just, you don't take a video or anything, or?
I think right now what we're doing is just taking, say, the first one as your reference.
I mean, you're just looking at, so you know that's a person because you were just looking at them.
Exactly.
Okay.
Yeah. There isn't any background suppression. So the basic idea would be subtract the reference from it. And also one other thing is that when this will be implemented in some sort of level crossing, so they will know the ground truth anyways. So we are still not sure that what they actually eventually want, because if a target is moving, that doesn't mean that we have to send an alarm. We only send an alarm if the target is moving inside the crossing.
Mm-hmm.
So we can just pick a area of interest and then just go along with that. So this is a human target moving away from the radar and then lying down.
Is this using both up and down chirps?
Yeah.
Okay.
It is using both up. And there isn't that much of a difference anyways when you process, because we are not doing any Doppler or anything, it's just plain and simple range profile. So as you can see, the target moves here and it disappears when it lies down. Now there are 2 human targets working parallelly towards the corner reflector. So that's the same thing. So right now we are trying to do some background suppression, just to see. So this is like very basic filtering. So this is the target. There is actually a trail here. So this is the target moving. And I think there is something wrong with the color bar here. It should be red.
Yeah, the color bars.
Yeah, so that's why it's not very clear. But we're just by some few basic MDI processing, we are hoping to just suppress the background clutter and move the C. So now the work has been about a month. So now what we have to do is, the processing that we did is everything was on MATLAB, but we cannot do that when we give them the software. So we have to convert everything in C, and not only C, they have this big guideline, MISRA-C, the motor industry guideline. So the software has to also comply with that. So the MISRA-C website doesn't have any specific compiler that they suggest that you should use this one, or specific tool to check the programming. So basically there is a forum, so you have to like pick and choose, go through the forum, but there are a few software companies who have made C compiler which automatically actually checks whether you are actually complying with the MISRA-C guideline. But those softwares are not free, so those are quite expensive. So we have requested for a trial version, a 30-day trial version. So, but they still haven't got back to us. Let's see. And then right now we saw that the radar can clearly see the moving targets and so on. So now what guidance wants is if it would be able to distinguish between targets of concern and targets that is not of concern. For instance, like right now we can easily send an alarm whenever there is a moving target within the area of interest. But that's not, I think, guidance wants. What they want is if there is say a human child inside the level crossing, then it will send an alarm. But if it's just a dog or a fox, then it won't send any alarm. So that's the tricky part because we are not using any Doppler information here. So if we don't use any Doppler information, then the parameters that we have are signal strength, then aspect ratio, and what else do we have? Signal strength, number of pixels, so speed.
Yeah,
Yeah.
and the track information if you start tracking the target.
Yeah. So the speed. So these are the few parameters that we can use to figure out that whether it's just an animal or it's a human target. So basically, it's just distinguish between human and non-human targets. That's the current idea right now. And after we do this, implement the whole algorithm in Mr. C in real time, then obviously we have to go probably to a real, not in a park, in a level crossing and to see if everything works. So if everything works, then that would be kind of like the end of the project. No. So that's the future work, and we have about around 3 months of time to do that. So, thanks.